Okay, hello everyone. So this week's video is on another slightly abstruse technical sort of subject, which is on the subject of what's called data alignment. Now, this is nothing to do with laying out of fonts in your text editor. It's nothing to do with whether your data is good or evil. This is to do with how the data is laid out in the computer's memory and why it can produce some slightly unexpected results sometimes. Now, the important thing to note here is mostly this is something that you don't really have to worry about as a programmer. If you're a programmer on certain types of systems, you might have to worry about it, but if you're working on those type of systems, you probably already know about this. This is not something that's going to come as a tremendous surprise. This really is a sort of look at what's going on behind the scenes of a computer. So the important point to note is we've sort of mentioned before that you can think of the computer's memory as this big 1D strip, and you have to look at it in other ways. If you want to look at it in other ways, you have to sort of do that yourself. So, if you want to represent a multi-dimensional array in the computer's memory, you have to map that onto that 1D structure in the computer's memory. Well, there are a lot of ways in which that idea of a big, undifferentiated, one-dimensional chunk of data is itself a simplification. And we're going to talk today about one of them, which is the concept of memory words. So word is a pretty common term in computing, but it's a slightly odd one in various ways, in that it's one of those sort of, here is something defined somehow sort of thing, rather than necessarily having a terribly deep and careful definition. So, for example, Wikipedia defines it as the natural unit of data used by a particular processor design. A fixed size datum handled as a unit by the instruction set or the hardware of the processor. Fortunately, we don't really need to worry about what it is. The important thing to bear in mind is that you can, for pretty much any computer, there are some weird ones where this isn't true, but for anyone you're really likely to encounter, you can define the concept of a word, which is a length in bits or in bytes. It's an amount of data, which is the primitive amount of data that the computer's CPU deals with. Usually it's the largest primitive piece of data that the computer's CPU can deal with. And the way most computers access their memory is they don't pull it in byte by byte, they pull it in word by word. And importantly, the words can't start anywhere. So this diagram really shows it. Here you have word 0, and then after it you have word 1, word 2, word 3, and so on. Words are usually a few bytes. So in a modern computer there are millions or billions, indeed, usually, of words in the computer's memory. But when you access a piece of data, the piece of data will not be pulled in itself. The entire word will be pulled in. And that's intrinsic. There's a lot of complications on top. Modern processors will try and speculatively fetch more data than they need and things, but running at its absolute most basic sense, going back to the earliest days of computers, words will be pulled into memory at once. So ignoring all of the clever stuff in a computer about caching and prefetching and other things, what that means is you want your data to line up with your words. So if you've got a piece of data here that's also, imagine each one of these boxes is a byte. So you have 4-byte word and you have a 4-byte piece of data. So long as this piece of data if this piece of data is the one you want, you load in this word, it's now all in the computer's CPU and ready to be used. If it's positioned here, similarly, you pull in that word, all of the data's there. The problem comes if it's aligned like this. So the first byte is in this word and the last 3 bytes are in this word. And at the very least, you now need to load both of those words into the CPU. And it is also worth pointing out that what the CPU has to do with this data is actually quite complicated. So it has to take the last byte of this word and store it as the first byte of the data. Then it has to take the first 3 bytes of this word and store it as the last 3 bytes of the data. So CPUs, to a very good approximation at least, don't run software themselves. So there is actually hardware in there. There has to be hardware in there to do this, to, say, take the last byte of this and the 3 first bytes of this and pack them together in what's termed the registers usually, which are the parts of the CPU that actually store data right before a calculation occurs on it. And not all CPUs have that hardware there. So if you go to the CPUs that are used in embedded systems, they may not have that hardware. And so if the data isn't aligned with these words, they can't use that data. And that's because every piece of hardware you put in the chip draws power. So if you want something to be, tiny and low powered, you don't want the hardware to do it. And famously, until the ARM v6 series, the ARM chip couldn't, used in phones and the like, couldn't cope with this sort of situation. Okay. So that's fine. What about if you're dealing with things that are smaller than a word? Well, here's a 2-byte data set. That's fine. It's at the start of the word. It works. I can happily put one here at the start of the next word as well, but I've wasted this space. These 2 bytes here are wasted. So in general, you might well pack 2 pieces of data like this in this sort of fashion. 2 in the low bytes, 2 in the high bytes of this word. You might choose to have them in separate words. That's perfectly valid. It'll work. But what you really don't want to have is them ever crossing these word boundaries. Now, obviously, same logic. You do need, if you have these 2 things packed in a single word like this, you do need some way of saying only use the lower 2 bytes or only use the upper 2 bytes. But there's actually very good reasons to want that anyway, for all sorts of reasons. So that's not a problem. So generally, this is how data alignment works. Data is aligned so that it either starts at the start of a word if it's the same length as a word, and this does happen on some systems. If a piece of data is longer than a word, then it'll just be packed into 2 adjacent words. And if a piece of data is shorter than a word, then it can be aligned within the word and packed together like this. Now, that has some complications as well. What in fact tends to happen is these words are always powers of 2. So they are either 2 bytes, 4 bytes, or 8 bytes on normal x86 hardware, depending on the generation. Modern systems, 64-bit systems, have 64-bit 8-byte words. And all of these data types are powers of 2 in length as well. So 1, 2, 4, 8 bytes as a rule. So as a consequence, what tends to happen is that these data sets are aligned on a multiple of their length. So these 2s, you can see, okay, you start here. This one then is 2 bytes in, which is 1 times its length. If you imagine that you have an 8-byte word, so these 2 are all part of one word and these 2 are all part of one word, then you could do it at 0, at 1 times its length, at 2 times its length, or at 3 times its length, and they all work. And that's generally true for all of them because they're all powers of 2. So that's showing what actually happens. Does it matter? Well, the answer to that is somewhere between yes and no. I'll sort of go through the no first. So historically, it really did matter. You had this whole thing where if these things were, not aligned correctly and crossed word boundaries, even processors that could deal with them had to do 2 memory fetches and, have some hardware that, packed them in. So you would use compute cycles, you would use memory cycles. It would slow the computer down. You could measure that slowdown quite easily. Modern computers with cache memory and with speculative prefetching and the like, rather less so, although still within the last, say, 15 years it has mattered, because some of the processor's instructions required this memory to be aligned. You could make an x86 processor, normal PC processor, work with unaligned memory, but it would be faster working with aligned memory, aligned in the sense I've just talked about. But that isn't really true anymore. Modern processors using modern vector instructions like the AVX series have both aligned and unaligned versions, and they tend to perform fairly similarly for quite a few years now. So as a general rule, the performance associated with memory alignment is not massively different, but it still hangs on and can be important in other ways, mostly because there's still enough cases where compilers worry about alignment that there are still things where data alignment is used. And I will now just show one of them. So this is something you may well have come across before. It's moderately famous. But I'm going to create a struct, and it's going to contain one float f. Remember, floats, 32-bit floating point number, 4 bytes of storage, and a double, which I'm going to call d. Okay. And I'm now going to create my main program, and I'm going to get it to print me the size. Name my struct. I'm going to call it demo. Okay. Now I've got a 4-byte plus an 8-byte data type, so that should come out at 12 bytes in length. But I run it and it comes out at 16. And the reason for this is because the compiler is aligning these data types. So the float is 4 bytes. So that goes from one of these word boundaries, because this is another feature of C and C++, which is that structs, they actually store the data in the order that you put them in the structure definition. And I'll come back to why that matters in a bit. So it puts this float first, 4 bytes, and it puts it at the start on a word boundary. This is a 64-bit computer, so it has 8-byte words. At which point it goes, okay, I'm now 4 bytes into a word, and I need to start a double. A double is 8 bytes long, so it needs to be aligned on an 8-byte boundary. That means it has to be at the start of a word. So I can't put it immediately after my float. I have to waste the other 4 bytes, or pack as it's generally called, in dummy space in those 4 bytes, and then my double will be correctly aligned for its own behavior. And so that's what's happening. It's literally just putting dummy information in between the float and the double. And you can see that because if you put it in yourself, if I put in 4 dummy bytes there, manually, the size doesn't change at all. Because a char, which is a single byte, doesn't have any alignment restrictions of itself. It's byte aligned, as it's often called. So if I put this here, these just pack nicely into that space that the compiler wants to leave after the float and before the double. So that's how alignment can come in. It can make things be not quite the size you expect, and that's important. But rather more importantly than that, it can sometimes make things larger than you expect them to be, even knowing about alignment. Because, as I say, C and C++ are absolutely strictly required to put things in these structures in the order that you define them. And there are very good reasons for that. There are very common programming techniques that actually rely on that behavior. But it can produce some odd results. So I'm going to leave my double, but I will take out the float. And I'm going to put in two chars. So I'm going to put in char C1 here and char C2 here. Now, given what I've just told you, you would expect that to be 1 byte and then another byte, because there's no alignment requirements for those 2 bytes. They'll be packed up together. It'll then have to waste 6 bytes because it needs to align the double on a word boundary. And so the whole thing will still be 16 bytes. 16 bytes. So am I correct? And the answer should be that I am. Okay, brilliant, I am. But watch what happens if I move my definition of C2 to here after my definition of D. It's now 24 bytes long. And 24 isn't perhaps a number that you'd have guessed, but the reason for it is these have to be done in order. So first of all, you have 1 byte. It then goes, right, the next thing coming is a double. That has to be on a word boundary. So I have to waste 7 bytes and put in the double. And I now put in my 1 extra byte, this char, afterwards. So what you'd immediately expect then is fine, it'll be 17. The reason it's 24 is because, in fact, it will pad the end of this structure as well. And it will pad it to the nearest multiple of the longest data type in it. Now, why it does that is a little bit more involved, and I'm not going to go into it. But this is the point. By just changing the order of these definitions in this struct, I have changed how much space I am using up. And if you're in a situation where you actually memory limited, again, this is often an embedded systems programming type thing, there's a good chance that you'll want to think about things like this. And basically, you store your data going up in size in your definition of a struct. So you'd have all your chars first, then all your short integers, then all your integers, then your long integers, and your long integers. And then after that, if you have arrays, you have the arrays. And this means that you pack as many things together as you can, because anything that's of the same type can pack end to end. That's how the alignment rules work. But that, of course, is slightly antithetical to good readable code. There might be very good reasons in a real code why you want these 2 parameters to be connected in some way. So that when you look at the source code and go, oh yes, I recognize those 2, those are connected. But that does actually have consequences for the code that the compiler produces. And it's very tempting to say that this is a C oddity, and the requirement of it is very much a C oddity. But if I go over here into a Fortran code, Fortran does not require that types be in the strict order that you put the elements in. So unless you do something. So if I create a type, I can make it be in strict order by using the bind C parameter, which makes it exactly the same as follow the C rules for building a type. This is what bind C does. But if I don't put that in there, my type my type would be, so if I don't put that bind C in there, Fortran does allow the compiler to reorder the internal structure of a type however it likes. That's one of the reasons you need that bind C. But if I actually put this in, so I put in real 64, D call it, and put in my C1 and my C2 again. So this is exactly the same structure. It's 1 byte at the front, an int32 int, then a 64-bit real in the middle, and then another 1 byte integer at the end. Create an instance of the variable. There we go. And I have to divide that by 8 because storage size in Fortran gives you bits rather than bytes. Nice. Okay, so if I compile that and run it, I get this same number 24 again, which is because Fortran has chosen to pack the data in exactly the same way, pack and align the data in exactly the same way that C has. And in fact, most Fortran compilers are very, very strict on requiring alignment. They quite often will not generate code that works on non-aligned memory, which can actually cause some problems with C Fortran interoperability if you're not careful. The Fortran standard would permit it to reorder this and put C2 here immediately after C1, but it didn't. And you can demonstrate that because if I put it in here, I get my 16 back. And so this is an example of how even languages that permit compilers to make optimizations, they don't always do it. And so that's it. That is memory alignment. Memory alignment is something that is worth knowing about. It produces some things that are sort of still important today, like that unexpected size difference between different ways of defining exactly the same data structure from a logical perspective. But it's not as important as it used to be for performance reasons, because more computers nowadays are happy to work with unaligned data. It is very important if you are an embedded systems programmer, because there are still some CPUs out there that require alignment. You can quite often still get better performance if alignment really does, if you really do follow alignment, but it's pretty small nowadays. I tried to find an example that really showed the effect, and I couldn't really find any that showed it reliably on a modern chip. But it's something that is worth knowing about, simply because it can cause unexpected effects in unexpected places. So it's just one of those things that it is worth knowing about, just in case at some point you encounter something where you have to worry about it. So we'll be back next week.